Hello, everyone. Welcome back to zkStudyClub. In this edition, we have Pratyush Mishra, a repeat guest. He is going to be talking about EOS, his efficient private delegation of zkSNARK provers paper that he co-authored with Alessandro Chiesa, Ryan Lemkool, and Nino Zhang from UC Berkeley. Pratyush, welcome back and take it away.
Hi. Yeah, thanks, Alex, and fantastic to be back. And hi, everyone. So sorry, I have a little bit of a cold, so I might be a bit lower in energy than normal. But yeah, so basically today I'll be presenting a paper, EOS, which constructs efficient delegation schemes for zkSNARK provers. Okay. Yeah, so this is joint work, as Alex said, with Alessandro, Ryan, and Nino. Okay, awesome. So probably for this audience, we don't need to go over SNARKs, but I'll still do like a quick overview. So basically, zkSNARK is this protocol between a prover and a verifier. The prover is making some claim that for some function f and partial input x to this function, it knows some private rest of the input w, or private input w, that satisfies the function. So you can think of f as being the function which checks that w is sort of the preimage of some hash x, right? Okay, so there's these two parties, prove and verify. The prover wants to convince the verifier that this statement is true. And what a zkSNARK allows the prover to do is to compute very efficiently a very short proof attesting to the truth of this fact, which the verifier can then take and check in time much shorter than the time it actually takes to run the function itself, or to run the computation itself, right? And the key property that we care about in this talk, besides the standard completeness, soundness, succinctness properties, is that of zero knowledge, which basically means that this proof reveals nothing to the verifier, nothing about W to the verifier, except the fact that this claim is true. So the only thing the verifier learns in the hash example would be that, okay, there is a prover knows the preimage for this public hash string X, right? Okay. Do we have a question in the chat? Okay, no. By the way,
sorry, Pratyush, just so you don't get distracted, I'll let you know if there's a question in the chat. I'll be welcoming people as they come in, and I'll just prompt you if something comes up, so that way you don't have to switch back and forth between your screen.
Okay, awesome, thanks. All right. Yeah, so the succinctness properties basically just says that the verifier running time is much shorter when the proof size is much shorter than the size of the function. Okay, so fairly standard things. So again, as everybody in this chat probably knows, in this call knows, is that there's been tons of applications of zero knowledge proofs over the past few years. I mean, also over the last 30 years, but specifically also in the last decade or so. So things like private transactions, private smart contract systems, sort of these decentralized multiplayer games which have hidden state but are running on public chains. Things like anonymous credentials. A bunch of other applications. And all of these sort of, in some sense, rely not just on the succinctness part of the SNARKs, but also on, particularly on the sort of zero knowledge part. Like they really rely on the privacy aspect of these proof systems. Okay. All right. There's like already a bunch of these applications. But sort of I suspect like the use of these systems in the real world has been somewhat hampered by the relatively poor proving performance of these the best proof systems that we have today, right? So for example, if you take ROV16, which was kind of the state of the art just a couple of years back, if you want to do like a simple task such as hashing some string with SHA-2, it takes say 140 seconds. This was on like my machine like last year. Probably has changed, but I sort of there's like this massive orders of magnitude gap between the actual computation natively on your computer and generating a proof for that same computation, right? And sort of you can get around this by doing some clever circuit design and stuff, but what most applications find is that there's still like at least a couple of orders of magnitude difference between running the computation natively and actually producing a proof for it. Yeah, this is sort of very limiting for, especially as you sort of move into more expressive applications such as these private smart contract systems where users will want to run or want to prove the execution of some arbitrary program, right? And it's sort of an end user trying to do this proof. So basically, all in all, it's quite important to use every trick that we can or every technique that we can come up with to really improve the performance of proving to remove it from the bottleneck phase, in these applications. Okay, so one approach besides really optimizing the proof system would be to try and outsource the proof generation from your potentially weak device to a much more powerful one. So say I have a mobile phone, right? And I want to generate a proof on it. At some point, I'll run into some performance, like the sort of the limitations of the CPU or of the memory, or the proof generation is eating up too much battery on my phone. So it's like a bunch of constraints, right? And you would like to minimize sort of these costs to allow you to scale to larger applications. Okay, so one idea would be to sort of say, okay, I'm not going to generate the proof on my phone. I'm instead going to outsource it, send over this proving task to some more powerful machine, say somewhere in the cloud. Maybe it's my desktop at home. There's a bunch of options. Okay, so I'll send over the public input and private witness to this powerful machine, and then that machine will do the computation and send me back the proof, which I can use in my application. All right. So okay, this works, but again, end up being limited by what your single machine can do. So people have come up with systems that allow you to sort of leverage the power of the cloud to its fullest extent and actually use multiple machines to collaboratively generate your proof, right? So instead of now a single machine, now I have like this cluster of machines, and they collectively will generate the proof for me. Okay. Okay, so we know how to do this. This is work from Wu et al. From a few years back, and it works. And like probably this was like the first work in this line. Probably today, if we took our modern techniques, we could improve on their results greatly. But overall, there's still a problem with this approach, right? Especially for these privacy-focused applications that I mentioned earlier. And the problem is that all of these workers, they learn what the private witness, my private witness was, right? Right. And in the scenario where these workers are located in some public cloud, the public cloud is now, if it is eavesdropping or whatever, it can learn my witness, right, and sort of de-anonymize me when I'm trying to use this application. All right. So ideally, we want a solution which allows us to do this outsourcing, but in a privacy-preserving manner. So the workers that I use, they don't learn any information about my witness. Right. So this is now our new goal, right? So we want to come up with some sort of delegation protocol or scheme where there's the prover, the mobile phone provides the public input and then some sort of obfuscated or encrypted or hidden version of the witness into the protocol. And then like there's some interaction or something goes on inside the protocol, and at the end, the phone gets back the proof that it wanted, right? And there's two goals here. So the first one is that efficiency. So we want to have privacy, but we still want it to be the case that the mobile phone is not doing a lot of work, because again, there are some constraints on the amount of computation it can do. So overall, its work should be much less than just generating the proof locally. And the second is obviously privacy, right? That at the end of this protocol, the delegator's witness should be entirely hidden from the worker. right? So it should not learn this machine should not learn any information about this private witness W. All right. Okay, so this is the setup so far. Any questions about the motivation or the protocol setup? Yeah, feel free to, I guess, ask questions in the chat or unmute or whatever is the appropriate protocol.
So no questions so far.
Okay, all right. So, okay, hopefully I've been very clear and people are totally understanding what I'm saying. But if not, again, yeah, feel free to stop. Okay, so this is our setup. We want to construct this delegation protocol. So let's see how we can try to go about doing this task. Okay. Now, unfortunately, when you have just a single worker, as far as I know, there's no way to really realize this protocol in this setting without using relatively heavyweight cryptographic tools like FHE. So, and the problem with these is that, or at least like some maybe limited homomorphic encryption, right? And the problem with these is that probably the act of just using this tool is going to make even the outsourced prover, like the work of this outsourced machine, much higher than if the like the end-to-end running time of the delegation protocol will be much higher than just running the proof locally on or generating the proof locally on your phone, right? So ideally, we want to have a system which avoids these heavyweight tools like FHE, but it's very unlikely that we'll be able to do this in the setting of just a single worker machine. So maybe we can relax our privacy goal a little bit and move to maybe a setting where we have a little bit more flexibility. And so instead of saying, we want to have just one machine and we want to have privacy against that one machine, we'll relax our goal and say, we'll want privacy against a bunch of machines as long as one machine is behaving honestly, right? So in our delegation protocol now, sort of the the delegator provides its witness in the obfuscated form as before. And then now these workers are sort of engage in some protocol with each other. And at the end of this protocol, they are able to generate the proof and send it back to the delegator, right? So the efficiency goal is the same as before. It should be the delegator's work should be much less than doing the proof itself. But the second goal is now changed. So instead of saying that we have one worker and we have privacy against that one worker, now we have a bunch of workers and we'll have privacy of the witness against these workers as long as one worker is honest and sort of following the rules of this delegation protocol, right? So sort of n-1 threshold. So, like in this case, up to 2 of the workers can be dishonest, but as long as one worker is honest and following the protocol rules, then things should be just fine. And we should be able to get the proof. It'll be a correct proof, and nobody will learn the witness. All right. So this is now our new goal, and maybe let's see how we can go about actually achieving this relaxed threshold privacy goal. All right. That's sort of the task of this paper. So what we do in this paper is to construct these delegation protocols for SNARKs that are based on polynomial IOPs. But I suspect also the techniques in this paper will generalize to other systems as well. But we focused on polynomial IOPs because sort of these are the most SNARKs based on polynomial IOPs, because these are the most, I guess, the state-of-the-art system that everybody's using in practice nowadays. All right. So in particular, we show how to construct delegation schemes or protocols for popular polynomial commitment schemes, such as the KZG and the bulletproof or IPA-based PC scheme, the Malin polynomial IOP, but I suspect it should be easy to do it for, say, Plonk also. And then sort of any SNARK, which relies on these components. So sort of our delegation protocol for the SNARK is in some sense generic you plug in the appropriate delegation sub-protocols for the underlying polynomial IOP and the underlying PC scheme, and you should be able to get out a delegation protocol for the SNARK as a result, right? And sort of this is our theoretical contribution. Along the way, we have some interesting results on what kind of tools you would actually need to realize this, even with malicious security. So even when your workers might deviate from the protocol, and we'll cover some of that today. But really the crux of it is that, okay, this is not just a theoretical construction. We were actually able to implement and evaluate these protocols, and sort of the takeaway is that delegating from a phone, we found was with our protocols was like up to 26 times faster than just running or trying to generate the proof locally on the phone itself, right? And furthermore, it allowed us to scale to proving larger instances and were provable on the phone itself, right? Because a lot of these SNARKs, they have high memory requirements. So even if you're okay with eating whatever time it takes, you're okay with that cost, you might still run out of memory when you're actually trying to generate the proof. So if you have a delegate, then maybe you can prove larger instances when you're not limited by a memory budget. Okay, awesome. So this is a checkpoint. So this is a summary of our results. I'll stop, drink some water, and also see if there's any questions. Anybody has anything?
There's no questions in the chat. The only question that I had, and I know you're going to get to this later, but maybe it's just interesting to state now, is what, obviously there's a lot of different mobile phones out there. So I guess, how should we think about this 26 times faster? Is this like my iPhone 14 or like a Nokia, like from last year?
So this was like a Pixel 3a or something.
Okay.
So it was like definitely not new. I think it was newish when we did the evaluation, which was like, so this paper has been in the works for a long time, like almost 3 years now.
So a relatively modern smartphone. I mean, not state of the art, but reasonably modern, probably with regards to probably the average of what the mobile phone technology level is for most of the world.
Yeah. So it's like I guess a slightly above the middle end phone, but yeah, it's also like it was like what new like 2-3 years ago. So now it's like somewhat old. Yeah. So I think it's if you took maybe a model phone, then the gap might be a bit less, but then also there's like a wide distribution in the power of these phones. So I think, yeah, this is the average number you would expect to see. And probably you're going to be more limited by the bandwidth that you have on the phone, because as we'll see.
So maybe this is a good point to ask, was this done on a 4G network or a 5G network?
On like a Wi-Fi network with,
okay,
say, 45, 50 Mbps connection, if I remember correctly.
Cool.
So slower than 5G, definitely.
Got it.
But so if you were to use this on data, then you would blow through your data cap if you had one very quickly. Unfortunately, there's like a large communication requirement. Basically, you have to, as you'll see, you have to send some like a linear in the witness size, like the R1CS witness size, for example, vector to the worker machines. So
cool.
And it would be good to see if there's a way to sort of work around that in future work. But yeah.
Cool. Thanks. I think unless anyone else has questions, I don't see any in the chat. Obviously, anyone feel free and just, I'm assuming Pratyush, you're okay. And also, just if you need to take a break, Pratyush, we need to pause for a few minutes to give your voice a rest. And so now you have a cold. Don't hesitate. Just, we can edit that out of the video. So don't worry about it.
Oh, thank you. Yeah, no, I think for the time being, I'm okay. But yeah, if I need to stop, then I will.
Great.
Okay, awesome. So, all right, let's see how we can actually go about constructing these delegation schemes, right? And sort of a natural starting point is this notion of multi-party computation, or MPC. Okay, so what is MPC? So it's basically a way for multiple parties to come together and sort of jointly compute some function f over their inputs in a privacy preserving manner. So in this case, there's these three parties, they have x1, x2, x3, and they want to compute f of x1, x2, x3. Basically, an MPC protocol allows them to do this while completely hiding all information about x1, x2, and x3, except for whatever is revealed by the output, right? So yeah, this party 2 doesn't learn anything about x1 and x3 except for this result, and same for the other parties. So yeah, no, this seems like kind of magical thing, but yeah, we've known how to construct these MPC schemes for the past 30 years almost now. And we have like some relatively efficient constructions, but just like SNARKs, efficient in this context means still like 100x slower than the native computation, right? But okay, they exist, right? And they are efficient in cryptographic terms. Okay, so let's see what one such construction would look like. And this is sort of based off of the speeds protocol, if you've heard of that. But I won't assume what that is. We'll cover what the construction looks like, right? So basically, this MPC protocol, the first thing you have to do is you have to express this function or this computation that you want to do as a circuit, just like in SNARKs, right? So it's like an arithmetic circuit over some finite field, like some z mod p or some prime p, right? And so if x1, x2, x3 are sort of the individual parties' inputs, then sort of you will run some computation over these x1, x2, x3 with some additional multiplication and equality and maybe some other gates, right? But sort of this is a standard arithmetic circuit model, nothing fancy, right? So how do you actually go about executing the circuit once you have it and once you have the parties' inputs? So the first step that each party does is it'll share its input using some secret sharing scheme. So what is a secret sharing scheme? So basically, it's a way to take your message M and split it into, if there's N parties, like N sort of related messages, such that as long as I am missing just one of these messages, one of these SIs, for example, the rest of the SIs reveal no information about the message M, right? So in the two-party case, if I don't have the other parties share, then I learn no information about the message that is supposed to be encoded inside the secret share, right? It's completely, perfectly information theoretically hiding, right? But the moment I get all of these shares, I can sort of add all of them up and reconstruct the original message, all right? So if I have all of the shares, then there's no privacy, but if I'm missing even one share, then there is full privacy. And so you can also define secret sharing schemes which have a more threshold notion of security. So, if I have at most, say, t-1 shares for t some threshold, then I learn no information. But the moment I have t shares, I can recover the encoded message M, right? But in this talk, we won't talk about those schemes, those Shamir secret sharing schemes, and we'll just talk about this very simple additive secret sharing where just you have to have all of the shares to recover the message. Okay, anyway, so that's background on secret sharings. So every party secret shares their x1, x2, x3 to all of the other parties using the secret sharing scheme. And then basically the parties evaluate the circuit gate by gate on these inputs, right? And how does this proceed? Well, for an addition gate, the key idea to notice is that these shares are additively homomorphic. So if I have a share for X and I have a share for Y, then I can just add my shares for X and Y, and I'll get a share for X plus Y, okay? So these shares have a very nice additive homomorphism. So if you're doing additions and linear operations in general, then there's no communication, things just work out fine. But if you want to do a multiplication gate, if you want to evaluate a multiplication gate, then there's a bunch of different kinds of protocols that you could use. So I'll just list a few of them. We won't go into any detail on how these actually work, but we can talk about it later if there's people are curious. So like these triple-based multiplication protocols, you could use linearly homomorphic encryption based protocols, oblivious transfer based protocols. There's like a bunch of these protocols which allow you to do this multiplication. But the common thing in all of these, the common property of all of these multiplication sub-protocols is that they require interaction between the parties. And sort of this really ends up being usually the bottleneck in using MPC. The moment you have a multiplication, you need to do a network round trip, right? Even if the computation is cheap, and it ends up being relatively cheap for many of these multiplication protocols, the moment you encounter a multiplication gate, you have to start interacting with other parties and sending information over the network, and basically incurring the network round trip time at least, right? Yeah, it's so really what you want to do in these MPC protocols is minimize the number of multiplication gates in your circuit, but also sort of minimize the number of consecutive multiplications. So when the output of one multiplication feeds into another multiplication, right? This is called the multiplicative depth. And really you want to minimize this multiplicative depth because it determines I guess the sequential like number of network round trips that you need to make at least. Okay. So yeah, that's really roughly how this simple MPC works. You know, most of the secret sauce is actually inside how you implement this multiplication, but we don't really care about it too much. And we'll see later on how we can realize in our delegation setting very simple protocols for doing this multiplication. Okay. So any questions on the model, on secret sharing, on anything?
If anyone has questions, feel free and jump in. But yeah, I don't see any, so I think we can just keep on rolling. Thanks, Pratyush.
Okay, awesome. All right, so this is the background in MPC. So sort of at first glance, this seems like the perfect tool to use to construct our delegation protocol, right? So what we do is we'll have these workers. So what we'll do is first we'll have the delegator sort of secret share its witness with all of the workers, right? So it'll run the secret sharing protocol to generate these, in this case, three secret shares of W, and send W, like the first secret share to worker 1, the second one to worker 2, and the third one to worker 3, right? And then these workers will run some MPC protocol for the circuit which corresponds to the zkSNARK prover, right? So you somehow encode your prover as an arithmetic circuit, and then you run an MPC protocol for it. Okay. So this seems like conceptually simple, right? And you might be asking, okay, why aren't we done? Well, the issue is that, as I mentioned before, MPC is, has some of the same limitations as SNARKs, and that the overhead is quite high. So one overhead comes from the fact that your circuit for the SNARK prover might be quite large. In particular, right, you need to support field operations, but also group operations and random oracle and hash calls, right? And it's not like you're doing like a small number of these. You have to do like a large number of these, for example, to compute MSMs, to compute FFTs, general polynomial arithmetic. If you're using things like lookup protocols, you might have to do some sorting in there as well. So basically, it gets the circuit itself can be quite large, right? So we would first have to figure out a way to, how to optimize this circuit. And secondly, even if you do that circuit optimization, you're still going to end up with some overhead just from the MPC protocol itself, right? So as I mentioned, these multiplications require interactions. So if you have a large number of multiplication gates in your circuit, or even a large multiplicative depth, you're going to end up with a lot of round trips in the protocol, which will slow you down. And maybe this doesn't matter for like a small circuit, but as you scale to larger circuits, you're sending a lot of information over the network in these MPC protocols, and you'll be sending at least like a linear in the witness size, information to the other workers. So you'll be running into some bandwidth constraints there. Okay, so you really want to figure out a way to reduce, make your multiplications as efficient as possible. Furthermore, like your MPC protocol might require some pre-processing. So for example, the speeds protocol does, and most of these pre-processing protocols require use of heavy cryptography, such as homomorphic encryption or some notion of oblivious transfer or other such schemes, right? Comparatively, like the online phase of these schemes is computationally very light. It just requires some field operations, like field additions and multiplications. So yeah, we want to figure out a way to reduce this pre-processing overhead. And finally, if we want to achieve malicious security, and it seems like a good goal to go for, we don't want our privacy to be compromised or the correctness to be compromised when the worker sort of deviates from the protocol in some way. So we would want like security against malicious workers. But for all of the schemes that I know of, where in this sort of n-1 out of n threshold scenario, right? Malicious security requires at least a 2x overhead compared to the semi-honest protocol, right? And so basically, if you use these schemes, you're immediately just leaving like 2x performance improvement for your delegation protocol just on the table right there, right? And in practice, this actually grows larger because you actually have to communicate 2x over the network, and your network might be slow, things like that, right? So as we'll see, like some prior work, which in this model, the best lowest overhead they can get is 2x compared to sort of local grouping. And we'll see in the evaluation how to get about this, okay, and how our protocol gets about performs. Okay, so the takeaway from this slide is basically, yes, we can try to use MPC, but there's these two obstructions that we need to overcome. First, we need to figure out a way to get like very efficient circuits for SNARKs. And second, we need to really sort of optimize our MPC for our application setting, maybe by taking advantage of particular properties of our application. Yeah, and generally sort of try to like really optimize the heck out of this, the underlying MPC scheme. Okay, so maybe let's see how we can do each of these tasks one by one, and we'll start by looking at the circuit optimization. All right, so our goal is to construct these efficient circuits for zkSNARK provers. And as I said before in this talk and in this paper, we focused on a particular kind of SNARK, namely that those which are constructed by combining polynomial IOPs and PC schemes. So this covers Sonic, Plonk, Marlin, all the variants of Plonk, all the subsequent follow-ups to Marlin, all of your PLOOKUP, lookup table protocols, everything sort of falls essentially in this paradigm, right?
And just to be clear on what, just for the viewers of this video, to be clear on what doesn't fall in this paradigm, this would be like the Fry-based protocols would not fall in here. Is that correct?
So you can technically also cast the Fry-based protocols, like something like so Stark or say Plonky2, as sort of using the Fry protocol in some sense as a polynomial commitment, but using but it's like it does require a little bit of a perspective change and doing some work to put it into that paradigm. But yeah, for other reasons, actually, we won't be able to support these IOP style protocols, in part because we sort of heavily leverage the homomorphic nature of our polynomial commitments, and PC scheme, and like say the Fry PC scheme, or the PC scheme that you could construct from Fry, is not
additively homomorphic.
Yeah.
Got it. That's helpful. Thank you. Sorry to interrupt.
No, fantastic question. Awesome. Right. So coming back. So basically in this talk, we'll we focus on these PIOP based SNARKs. And let's do a quick recap of how these work. So basically there's this polynomial IOP component, right? So think like the polynomials in Plonk or Marlin or whatever is your favorite polynomial IOP. So your SNARK prover runs this polynomial IOP prover to get out some polynomials, and it invokes this polynomial commitment scheme to commit to these. And this happens over a bunch of rounds, at each round, the verifier in turn runs the polynomial IOP verifier to generate some challenge or some randomness or whatever, sends this over to the other side, and this happens a bunch of times until sort of we're done with generating polynomials and we have all of our commitments. And at this point, we want to show that, okay, these polynomials inside these commitments have some relation, they satisfy some identities or whatever, right? And we'll do this by querying these identities at some random points, essentially, right? So we ask for the evaluations of the committed polynomials at some evaluation points, and we show that these evaluations are actually the correct evaluations by using an evaluation proof or an opening proof that is provided by these PC schemes, okay? And sort of you generate this evaluation proof along with the corresponding evaluations, and you send this over to the verifier, who can invoke sort of some decision procedure on these evaluations, and also will check the evaluation proof to make sure it's actually valid, that the evaluations are correct. Okay, this is an interactive version for all of the polynomial IOPs that we care about. They're what are called public coin polynomial IOPs. So you can sort of replace the verifier with a hash function, and this is the Fiat-Shamir transform. Okay. So this is a high-level overview of these PIOP and PC plus PC SNARKs, right? And this is the paradigm underlying Sonic, Planck, Malin, etc., as I said. Okay, so this is the construction. Let's take a slightly deeper look at what operations are performed by the SNARK prover in this type of construction, right? So focusing first on the polynomial IOP prover, right? Well, it's a polynomial IOP, and the output of the prover is polynomials. So you can imagine, you're doing some kind of polynomial arithmetic where the polynomials are defined over some field, say FR, right? In particular, like you're doing a bunch of operations such as FFTs, things like sum checks. You're doing polynomial evaluation, polynomial interpolation, basically a lot of arithmetic with polynomials. And these polynomials have degree that's linear in your witness size, at least, right? So, for efficiency, what we want is that our circuit that we designed for our SNARK prover, it really should natively support operations over this field FR that's used by the polynomial IOP prover, right? Otherwise, you're doing some sort of non-native arithmetic, which is quite expensive. I mean, it's expensive in SNARKs, is going to be much more expensive in MPC, where it's more difficult to use tools like lookup protocols as well as custom gates to reduce the overhead. Okay, so ideally we want to support native operations over FR. All right. Okay, so that's the constraint from the PIOP side. What about the constraint from the polynomial commitment side? Well, looking at popular polynomial IOP such as the KZG scheme or the sort of bulletproofs or inner product argument-based PIOP that's underlying, say, Halo 2, right? What we see is that these polynomial IOPs, they require, they do a lot of elliptic curve operations over an elliptic curve whose order is R, right? So which has a scalar field equal to FR. And now for security, unfortunately, these elliptic curve operations themselves require, some field arithmetic, some underlying field arithmetic. But this underlying field arithmetic is over a field FQ, which is different from FR, right? So each elliptic curve addition, elliptic curve doubling, or whatever you're doing, right? It requires operations over a small number of operations, but still some operations over FQ, which is not equal to FR. All right. Okay, but again, still we're doing a lot of these elliptic curve operations. You're doing linear sized MSMs, for example. So you would really want to sort of be very efficient and have your circuit also be native over FQ somehow, right? So you want it to be native over both FR and FQ, right? And Unfortunately, we don't actually know how to do this. This is a problem we'll see how to resolve in the next step. Okay. So this is the issue from both the PIOP and the polynomial commitment side, but we also have to compute this random oracle in some sense inside our circuit, right? And doing this would require us to somehow instantiate the random oracle with some sort of MPC or SNARK friendly hash. But unfortunately, even the most efficient hashes that we know of still have relatively high multiplicative depth and a large number of multiplications. So yeah, sort of we're limited by we'll have some. Okay, we're not doing like the hashes are not of like a large amount of data, but still we'll be the sort of our sequential, right? So we can't proceed to the next round until we've computed the Fiat-Shamir hash for that round. So we're waiting, like we have to wait at least for the multiplicative depth of the hash circuit before we can proceed with the rest of the protocol.
We have a question in the chat from Dara. I guess, Dara, do you want me to read? I'll pause for a second unless if you want to just say it yourself. Otherwise, I'll read it. Okay. The question is, okay. Yep. So the question is, does using a cycle of curves help?
Oh, that's a good question. So I haven't really thought about it. So maybe it could help, but so like unlike SNARKs, where sort of your the SNARK construction itself restricts you to using a particular elliptic curve, right? Here, the MPC protocol doesn't necessarily. It's not like the implementation of the MPC protocol internally uses an elliptic curve, right? So I suspect maybe there's like some interesting protocol that you can develop that uses a cycle of curves to avoid, to sort of get around this requirement of FQ not equal to FR. But I suspect we have more flexibility here compared to the SNARK setting, and so we don't have to resort to tools like the cycle of curves.
Great, thanks.
Okay. Yeah, but yeah, it's a good question. Maybe there's some interesting protocol ideas for future work that we can leverage. Okay. All right. So we have these three constraints. We have to compute FR arithmetic. We have to compute these group operations. And we have to compute these random oracles. All of these efficiently, right? So let's see how we can get sort of resolve all of these constraints simultaneously. And resolve this problem of supporting multiple kinds of these operations, right? And then after that, we move on to, okay, how do you actually, once you figure out how to support these operations, how do you support lots of these operations efficiently, right? So these are the two problems that we have to tackle. We're doing on time. Okay, so 9:50. Yeah, probably I think I'll take another 20-ish minutes, which fits within our time profile.
Great. Yep.
Okay. Oops, there's this row, which is just mysteriously on the slide. But okay. So the key idea that we'll do is to sort of that we'll use is so take inspiration from some prior work and sort of generalize our circuit model. So instead of just saying we have a circuit where we only do field operations, what we'll do is we'll extend our circuit model and add in new gates, which do, for example, group addition and group scalar multiplication and random oracle calls, right? And these will sort of be like native operations that we can do inside our circuit, right? So now in our circuit, you might say, okay, I'm going to add x1, which is a field element to itself, right? But then I'll multiply that result of like this 2x1 with like I'll do a scalar multiplication of x1 with some group element, right? And then I'll take that result and I'll feed it along with x3 into some random oracle, right? So this will be this is like basically like a generalization of our previous circuit model. We've extended it with some more gates in the basis, right? Okay, so you might be saying, okay, we've sort of just shifted the problem to another layer of abstraction. We sort of just said, okay, now our circuit natively supports these things. But let's see how we can actually, once we have this shift in perspective, how we can design efficient MPC protocols for this generalized circuit. Right, and sort of the key idea that we are able to leverage is that additive sharing is linear, right? As I said before. And I guess the key way to leverage this insight is that what I'm additively sharing doesn't necessarily need to be field elements. It can also be now group elements, right? So I can take a group element, say M, and I can secret share it into a bunch of group elements like S1 through Sn, right? Each of these is themselves a group element, right? And the idea is that if I have up to n minus 1 of these group elements, I get no information about M, right? But the moment I get all of the sort of secret shared group elements, I can add them up using group addition, right? And then I will be able to recover the underlying group element message M. Okay. And roughly the sort of, okay, maybe I can explain what the secret sharing scheme looks like. So for a finite field message M, right, say for two parties, how I would do the secret sharing is I would sample a random R, and I would send to party one M plus R, and to the other party I would send R, right? And the idea is that to the party which received R, okay, it's just a random field element, it reveals no information about M. And to the party which got M plus R, that part, like the M plus R itself will look like a random field element because sort of you're taking something and you're adding in completely something random. And so basically you're ending up at like a random spot in the field. So that's how you get privacy. This is for field elements, right? But the same idea extends to group elements also, right? So I take my message, my group element, right? I'll sample, say, like a random group element, call it capital R, and I'll send to party one, capital M plus capital R. And this will again look like a random group element. I'm just adding in something random. And to the other party, I'll send R. Now, so far, like, yeah, the sort of the argument for privacy goes through as before. And again, you can add up M plus R. Okay, I would actually send M minus R and R. But if you add these two things together, the R's will cancel out and you'll get out your message M, right? So basically, the key insight is that the secret sharing doesn't actually require you to be over a finite field, but like for the more, I guess, algebraically knowledgeable, I guess, which I am not, but basically like these additive sharing schemes, they also work over modules. So FR modules, and the elliptic curve group is an example of a FR module, and a module is basically just something where you can add things together, and you can also do scalar multiplication, essentially. So that's a high-level takeaway. But yeah, basically all you need is like something which has this additive structure of like additive group structure of order R, right? And your elliptic curve group has order R. The additive subgroup of the field has order R. So basically you can move between these and extend your secret sharing scheme to both of these settings. Okay, that was quite a mouthful. Any questions on this? Basically, the idea is that, yeah, you can take your additive sharing scheme over field elements and you can sort of shift it to work over group elements also. And sort of you get the same guarantees and everything.
Cool. No questions.
Okay, so, awesome. Hopefully everybody is following along. All right. So this is like
I lied. We have one question.
Yeah, awesome. So does needing to use scalar multiplication cost a lot more? So that's a good question, right? And what we see is that just like in the finite field case, right, where if I'm doing a multiplication of a secret shared element by a public element, right, then it doesn't require actually any interactions. So if I have some element, public element C, and a private element, secret shared element X, then I can compute the secret share of C times X just by locally multiplying my share by C. All right. Similarly, in this setting, if I have either a private group element G that I'm trying to do a scalar multiplication with a private element, private field element, or vice versa, like I have a private private field element and a public group element, then sort of you can just use your standard double and add algorithm natively to compute the scalar multiplication. So you're not actually your cost for executing the scalar mul gate is going to be the same as the cost of doing it locally, and there's no interaction involved, nothing. Yeah, so I'm just going to cover this literally in the next portion. Okay, so to evaluate the circuit, this new generalized circuit, we proceed as before for field elements. Okay, I'll get to your question there in a second. But okay, so for field elements, things are changed as before. For group elements, yeah, sort of again, we are able to just locally add our shares of the group elements, right? But for multiplication, the scalar multiplication operation, right? You can sort of, again, do this native scalar multiplication of this, say, public element y by the share of x, right? And then now you'll have a share of x times y. Or you could do it reversed also, like, you could scalar multiply public x by the share of y, and now you'll have a share of x times y. So the follow-up question that Dara asked in the chat was, if both x and y are public, in the small scalar multiplication case, do you have any additional cost? And the answer is no, right? Because there's nothing to hide in that case, so you can just execute it locally yourself, right? And you don't need MPC for that. So public scalar times public point is completely there's no MPC involved at all, right? And in some sense, you can actually pre-compute it before you start the MPC because both x and y are publicly known. And sort of then you can hard code this value inside your circuit, just like sort of the case of say these constants in zkSNARK circuits. The same idea would apply here. Okay, yeah. So this is how you would evaluate these addition gates for group operations, and similarly the multiplication gate for group operations. Double also is similar to like the addition gate. You would just do like a local doubling using a standard doubling algorithm for elliptic curve. Okay, so that's the group operations taken care of. Okay, I guess the question is, if we have this restriction that y is public, right, or the group element that we're using in the scalar multiplication gate is public, and you might wonder, okay, is this actually a restriction in practice? And thankfully, as we'll see, it's not really a restriction, because for all of the SNARKs that we consider, the scalar multiplication essentially happens between the some secret point, like your witness, right, and the SRS. But the SRS is sort of publicly known to everybody in the world, right? So it's a public point. So in practice, for our applications, there's no restriction on this restriction of the y being public is not actually a restriction. Maybe there are some other applications where your group element might itself need to be private, but that's something that we don't consider for this use case. Okay. All right. So the last gate is random oracles, and okay, I won't exactly cover this right now. We'll see how to efficiently realize or evaluate random oracle gates a bit later. Okay, all right, so resuming this model, basically what we've done is now we've sort of cut the knot, and now we don't need to have FQ operations over in our circuit, right? We can get by with just doing FR operations only inside the entire circuit, and so we'll get like really high. It seems like we can get like a really efficient circuit for the zkSNARK prover, right? In some sense, also, this extends, like okay, maybe I'll go on to the next step, right? So now we have to figure out how we will realize these efficient circuits for these polynomial IOP provers. Yes. So that's problem one solved. And like, how do you actually support these different kinds of operations? The second problem is, okay, now we have lots of these operations. So how we support them? How do we actually get a circuit which has all of these many operations supported efficiently, right? So to do that, let's take a look at the kinds of operations that are performed in, say, the PIOP prover circuit. Okay. Oh, I got the animation order slightly off on this. Yeah, I'll just fast forward through all of the animations. Okay, so if you look inside a common polynomial IOP prover, you're doing a bunch of operations such as evaluating P over some multiplicative subgroup, you're multiplying P by a scalar, you're interpolating polynomials, you're adding two polynomials, you're multiplying polynomials, you're dividing polynomials, like all kinds of polynomial arithmetic is going on, right? But the key insight that you can really take advantage of is that for everything except multiplication of two secret polynomials, basically all of the other operations that are performed by polynomial IOP provers, they are in some sense linear operations and can be realized only with addition gates, right? And what this means for our scheme, for our sort of cost model, is that actually doing these computations only requires local computation, doesn't require any interaction between the workers or between the parties of the MPC protocol, right? And because you're only doing it locally and you're just doing your standard field operations, you can get efficiency that is roughly on par with the efficiency of the plain text prover, right? So for these operations, you're literally as efficient as the plain text prover would be outside of MPC. But what about this polynomial multiplication, right? So if you look inside what a polynomial multiplication looks like, essentially you have to do FFT to sort of put let's say you're starting off in coefficient form. You do an FFT to go to evaluation form for both of your polynomials, and then sort of you do a pointwise multiplication on all of the evaluations, and then you would do an inverse FFT to go back to coefficient form if you need to, right? Now, the cool thing is that the FFT is a linear operation, right? So we don't actually have to execute it again inside MPC in any way. It's going to be an entirely local computation, just like these other operations. So for the FFT and the inverse FFT, we're completely fine. There's no additional cost. However, we do have to do this pointwise multiplication, but and we have to do like a large number of these, like up to the degree of the product, right? But the nice thing is that all of these can be sort of done in parallel. So the multiplicative depth is still just very low. It's just 1, because you're doing sort of a bunch of independent pointwise multiplications, right? Like the multiplication for the 100th evaluation, like the pointwise multiplication for the 100th evaluation is completely independent of the pointwise multiplication for the first evaluation, right? So you can do all of them at the same time in parallel. So you're able to sort of saturate your network bandwidth as much as possible. And you end up having low multiplicative depth, right? So you're not paying a lot for network round trip cost here. Okay, so basically the takeaway is that for polynomial IOP provers, most of the cost is going to be equal to the cost of doing the plain text prover locally. And then for polynomial multiplications, okay, maybe you will have a little bit more cost. But the good thing is that for a lot of SNARKs that we care about in practice, such as say Marlin or like the the 3-arity, the 3-column version of Plonk, we only have to do one polynomial multiplication, right? So we're able to avoid high multiplicative depth. Or even if you have more polynomial multiplications, you can, again, they're sort of independent multiplications, so you can do them in parallel, essentially. Okay. Any questions about this? I don't see anything in the chat, but maybe we'll stop for a second.
Nope, I think we're good.
Okay, all right. So that's the polynomial IOP prover. The summary is that it's basically as efficient as the local PIOP prover. Okay. All right, so now let's try to design efficient circuits for PC schemes, right? And we'll focus on this slide on KCD just because it's very efficient. It's very simple to describe, and it's also efficient and used a lot of SNARKs. Okay, so our goal in this slide is to basically say, okay, I have a secret share of a polynomial, and I want to go from the secret share of the polynomial to a secret share of the commitment to the polynomial, right? So how would I go about doing this? So what I would do is, okay, I have my SRS, which is the public group elements, right? And I have my polynomial, which is basically a list of coefficients in secret shared form. So this is private information. Now, to compute the secret share of the commitment, I would basically just compute the MSM like standard, right? So I would take these coefficients AI and multiply them with the respective elements in BI and sum all of those results up, right? And if you recall, this is a multiplication of a private scalar by a public group element. So this is a linear operation, right? It doesn't require any interactions between the workers. And so each of these individual scalar multiplications is interaction free. And now we're just adding up a bunch of shares of group elements, which is again a linear operation. So it ends up being overall completely linear, right? So we can compute this entire commitment in a local manner without having to interact with anybody else on the network. And I'll be able to get my commitment, my share of the commitment very efficiently. Okay. And you don't have to actually, you don't actually have to do the individual multiplications and then sum up the results. You can use a protocol or an algorithm like pipinjaz even in the secret shared setting, and it just works out fine. Okay. So that's the commitment. What about the process of computing the opening proof, right? So now we have the secret shared polynomial, and we have a public point. So let's say we know what the point is that we're going to be computing the evaluation proof at. So the first step will be to compute this witness polynomial. And this involves doing the division of a private polynomial by a public one, right? This x minus z is a public polynomial. And fortunately for us, this is, again, a linear operation. You can think of it, one way to see why this is linear is, for example, if you try to do the polynomial division using the FFT method, right? So you compute the FFT, you use the FFT to get the evaluations of the numerator and the denominator both, right? And you sort of invert the evaluations of the denominator, and then you do the pointwise multiplication as before, and then you do the inverse FFT to get back the division result. But the thing to notice here is that now in the pointwise multiplication, right, you're multiplying the private evaluation of the numerator by the public evaluation of the denominator, right? So you're doing a private public multiplication, and this doesn't require any interactions, right? So it's a linear computation. And so we can compute this witness polynomial without any interaction again. So we have multiplicative depth 0, no multiplication gates. So this is fantastic for our efficiency. And then we compute the commitment to this witness polynomial as before. And this is, again, an entirely linear operation. Okay. And this gives us the secret share of the evaluation proof. Okay. So yeah, we're heavily sort of leveraging the fact that in some sense, KCG is additively homomorphic. So if you want to compute, and so the idea now is that I can just add up these commitments, these shares of commitments to get out like the commitment to the actual polynomial P. All right. So the takeaway from this slide is basically for KZG, you can get complexity, which is on the same order as the sort of, actually exactly the same as plain text KZG outside of MPC, and there's no interaction.
I have a question. Is this the same for the IPA schemes, or is this unique to KZG?
Yeah, so for IPA, the commitment is the same because again, it's like sort of essentially a pedersen commitment, right? So there's you have the same property there. For the opening, it's a bit more involved because yeah, you have like these interactions like random oracle calls in the middle, right? It's like a logarithmic round protocol. So there's a little bit more involved, and you need to communicate essentially like in the protocol that we have, maybe it's like more efficient protocols, but you have to communicate between the workers like a linear in the degree sized vector between the workers. But the cryptographic cost, like beyond that, is the same as a standard IPA. So it's once you do some, essentially you're trying to blind the commitment that you're opening, and you need to do the blinding in like a secret shareable way. Once you've done that, though, like you're basically doing the IPA over like a publicly known polynomial, which is blinded. So the blind, like even though it's publicly known, the blinding ensures that no information is leaked. But then sort of you can proceed with sort of the standard public coin, like the standard IPA. So even in that case, there's like one round of interaction, but like the majority of the work, which is the MSMs and all of that stuff, is very much the same as the plain text IPA based PC scheme. Yeah, so that's a great question, Alex.
Thanks.
Okay, I think there's one more question from Dara in the chat.
Saw that. Great. Yeah, go ahead. If you see it, you feel free. And yeah, can you just read the question so the video people can hear it?
Yeah. So the question is it important to reduce the number of PIOP rounds as far as possible? And sort of generally, kind of yes, but in practice, it doesn't matter too much because the cost of the prover. Okay, so the aim of reducing the PIOP rounds would be to reduce the number of random oracle calls eventually, right? Like that is the main benefit of having a lower number of rounds. The downside, though, is I guess not the downside, but rather like the performance characteristic of our MPC scheme is that we'll be able to realize these random oracle gates essentially by involving the delegator, by doing the interaction with the delegator. And okay, so you'll have to pay like a network round trip time interaction with the delegator, but it's like, okay, for all of the protocols that we know of, it's like a logarithmic number of rounds, right? So, okay, you'll have to talk to the delegator like a log number of times, but that's like, okay, like your MSM is going to cost much more than it takes to sort of send a small message to the delegator and get the response back. So yeah, anyway, like in general, it's beneficial to reduce the number of rounds of PIOPs, and the same cost analysis applies here also, but it's not like a larger, like it's not more critical here in some sense. Okay, so essentially now we have these efficient circuits for the PIOP scheme and PC scheme. Okay, I guess there's one more question from Dara. So the question is, does the number of rounds, is it basically the same as the sort of standard SNARK in that there is, it's like the same number plus maybe like some small additive constant. So I think it's a good to keep in mind here that a goal here is that sort of the end proof of this protocol should look in some sense identical to as if I had computed the proof locally. I should have mentioned this earlier, but our goal here is that the end proof looks identical to like the actual proof as if I had computed the proof on my own machine. So it should be indistinguishable to somebody else looking at the proof. They should not be able to figure out, oh, you know, this proof was actually computed using a delegation protocol. We want to avoid that. So the end SNARK has the same number of rounds, the same complexity, like verification complexity. Everything is entirely the same as the PIOP scheme, as the sort of underlying plain text SNARK. So there's no change in number of rounds there. In the MPC protocol, though, yeah, so this analysis actually applies. So the number of interactions between the workers and the delegator and all of this stuff is ends up being, yes, like the number of rounds in the PIOP plus like some small constant, usually. So that is the analysis for these for our, at least our delegation protocols. So that's a good question. That's very good to clarify this. Awesome. Okay, so we are running a bit.
Just quick time check. So we have about 15 minutes left of the session here. So just wanted to give you a heads up there.
Yeah. So I will. I think. Yeah, we should be able to cover things very quickly.
We always save the heavy hitting questions for the last 30 minutes. So in an attempt to foil your ability to end on time.
Well, that's where all the meat is. So it makes sense, right? Everybody knows what a SNARK is. Nobody's asking, oh, what is the proof size in a SNARK? Well, everybody's asking, how does the scheme actually work? So it makes sense. Okay. So a lot of these techniques are not sort of super novel. Though again, because the paper has been in progress for almost 3 years, we've seen these results pass us by in some sense. But yeah, these techniques have also appeared like in prior work, such as the ones that I've listed below. And again, I guess it's not very useful. I can provide slides afterwards, which has the links embedded inside. Okay, so maybe let's summarize our progress so far. Okay, I guess I'll be taking a step back. So we had efficient circuits for polynomial IOPs and PC schemes, and essentially and okay, I didn't talk about the random oracle stuff, but the idea is that once you have these efficient sub-circuits, it's very easy to stitch them all together and get a circuit for the overall zkSNARK proof. So get this c-SNARK circuit. All right. So we've designed now this efficient SNARK, but if you apply this to our MPC protocol, which now supports these scalar multiplication gates and so on, we're only sort of achieving efficiency that is, on par with this prior work that I mentioned on the previous slide, right? And the question is, can we do better? Can we sort of tailor our MPC to avoid these slowdowns, right? And let's take a look at how we can actually go about it. So the answer, spoiler alert, is yes, but it's somewhat non-trivial, right? And the two sort of opportunities that arise in improving or specializing our MPC for our application use case is, the first one is to sort of take advantage of this asymmetric threat model, right? So in most MPC protocols, sort of each of the parties, they're sort of equally distrusted, right? Like no particular party has like a privileged position in the protocol execution, right? So you can't like trust that like any particular party to do special parts of the protocol. However, in our application setting, we have one party who is always honest, right? They will always follow the rules of the protocol, and that is the delegator, right? It doesn't make sense for the delegator to cheat because, okay, what will it gain out of it, right? Okay, at the end, maybe if it cheats, it'll get out an incorrect proof, but then it's sort of wasted its own time, wasted probably money to run the cloud proofers and all of this stuff. So, good question. Can we trust ourselves? Let's assume that we can. If we can't, then there's lots of problems that we'll have to solve.
Well, I guess it's important here that you're producing a proof that is the same essentially as the underlying scheme. So then it's as sound as the underlying scheme.
Yes. So that we will actually leverage that property also, right? But the idea is that so we have this party, this delegator who is always honest. Okay, it's a bit computationally limited, it can't do heavy computations, but we can trust it to always follow the rules and sort of want to preserve its own. It'll be incentivized to preserve its own privacy, right? And so we can maybe try to leverage this delegator to do more efficient protocol design. So that's the first opportunity. The second opportunity would be to sort of somehow try to take advantage of the kind of computation that we're doing, right? And what I mean by this is that if you look inside, see like the circuit that we're computing, it's computing a SNARK, right? And the point of a SNARK, as Dara mentioned, right, is that it's supposed to be sound, right? So if the question that we want to ask is, if one of these worker machines sort of deviate from the protocol in some sort of non-trivial fashion, like, will they be detected by the fact that, okay, maybe the SNARK will just fail to verify, right? So maybe if we add a check for SNARK verification at the end of the delegate checks that the SNARK it obtains is actually valid, then we'll be able to detect some malicious behavior on part of the workers, right? And so then can we use this to get cheaper security guarantees against malicious workers, right? And sort of reduce that at least 2x overhead that arises from existing malicious security techniques, all right? So these are sort of the two questions that we want to ask and see whether we can, make some headway by taking advantage of these two opportunities. And let's go over them one by one, right? So first we'll start by looking into how we can take advantage of this asymmetric threat model. Nope, oops, I'm supposed to animate that. But anyway, let's see how we can do this by sort of trying to design more efficient protocols for multiplication gates, right? So remember, the point of a protocol for the multiplication gate is that if worker A and worker B have shares of X and Y, then they should be able to obtain via this multiplication protocol shares of the product Z, which is equal to X times Y, right? That's the goal of any multiplication protocol. And so there's like in the literature, there's like a bunch of these protocols for doing multiplication in sort of the standard NPC setting. One example, which is sort of used, for example, in the SPEEDS protocol, is sort of a multiplication protocol which has some pre-processing step that happens in the offline phase and is independent of the X and Y that you actually want to do the want to multiply. Okay. So in this offline phase, what the workers do is that they will run some pre-processing protocol and get out some pre-processing material A and B, which they'll be able to use in the offline phase. In the online phase. But the downside is that this pre-processing protocol is usually quite heavy, right? It'll require, say, something like a bunch of OT operations or oblivious transfer operations, or a bunch of homomorphic encryption operations with like some tailored zero-knowledge proofs of correctness about the ciphertext and things like that, right? So overall, it's like, not very clean, very, very heavy. All right. So this pre-processing protocol is heavy. The cool thing is that the online phase is very cheap, right? This pre-processing material is basically looks like a bunch of secret shares. And so when you want to do the online protocol, it's basically doing like some very cheap field multiplications and additions, right? So really the bottleneck in these protocols is this pre-processing step. So ideally we want to be able to remove that. And sort of, I guess the cute insight that we had was, okay, you can just replace it with the delegator itself. But the delegator will just generate the pre-processing material in the offline phase, give it to the workers, and then they can use that during the actual proof generation phase to compute any multiplications that they need, right? And so you need like a linear amount of this pre-processing material, like linear in the number of multiplication gates. But again, you can just do this in an offline phase. So it's like, when say your phone is plugged in overnight, right? That's when you do this pre-processing step to generate the material for your workers, right? And the cool thing is that, or I guess even cooler thing is that if you have the delegator doing this pre-processing, you actually don't need any of this heavy cryptography. You can just get by with some finite field multiplications and additions. So concretely, for people who want to look later on, this pre-processing material is called multiplication triples. It's a very common technique in the NPC literature for doing multiplications. But you can generate them very efficiently if by yourself, if you trust yourself, right? But if you didn't trust, if there was no sort of trusted party to generate these triples, you would have to use this heavy cryptography to do that instead. Yeah, so I know we're 5 minutes in. I'll wrap up very quickly. Okay, so there's also another protocol that you could do. Basically, instead of using any of this pre-processing, you could just have the delegator perform the multiplication. The workers send their shares to the delegator combines them, reconstructs the values, and performs the multiplication and shares the multiplication results back to the workers. The disadvantage of this is, compared to the previous one, is that now you have higher delegator worker communication in the online phase, which you might want to avoid, or maybe you don't care. Like, and this is simply that you don't need any pre-processing step. Okay, so this is another example of how you can leverage the delegator to really cut out any heavy cryptography. Okay, again, my animations were off. I'll have to go back and fix all of these things. Okay, so I talked about multiplication gates. I had mentioned earlier that we would see later on how you would realize a random oracle gate. But again, the idea here is very simple as before, right? So when I want to evaluate the random oracle on some private input X inside my circuit, what I'll just do is I'll have the workers send the shares to the workers. I'll have the workers send the shares to the delegator. The delegator will reconstruct the input, compute the random oracle over it, and send back the random oracle output, either shared or not shared. It depends on the use case. In this case, in SNARKs, we don't need to hide that the random oracle output generally. So the cool thing is now by doing this, we're able to completely avoid hashes inside the MPC protocol, and so we're like at native efficiency.
Right, I guess because the random oracle outputs are public coins.
Yeah, exactly. Yeah, so they just look like random things, and they don't really reveal much information about anything. Okay, so this is how you would do random oracle gates. So overall, by doing this, we're able to get the end-to-end MPC protocol, which avoids any heavy cryptography. So it's like uses basically PRGs to do delegation, right? And that PRGs are only there for reducing the cost of the secret sharing step. You can avoid them. Whereas like we don't know in like the standard MPC setting how to get n-1 out of n security with just say PRGs. You need to rely on some public key type operations, as far as I know. Okay, so we have 3 minutes left. I will rush through this next part. But sort of the next step is to use the other. Yeah, I'll get to Dara's question maybe after this portion. Okay, so the overhead in a lot of these MPC protocols for malicious security is quite high, right? So one approach to achieving malicious security is, for example, to use specialized zero-knowledge proofs to prove that you computed the message at that MPC round correctly. But zero-knowledge proofs are quite expensive, and even sort of the most efficient protocol speeds uses these algebraic MACs, which at the very least double the amount of communication and computation, right? And so this is reflected in this prior work by Ozdemir and Pone, which in their protocol they incur at least a 2x overhead compared to proving locally, right? So the best overhead they get is 2x, and as their bandwidth degrades or the number of provers increases, this sort of gap actually goes up, right? So they have larger overhead compared to local proving. All right, so the question is, can we do better? And the idea is that actually, yes. And to do this, let's go back to this sort of idea of using ZKPs to prove that I've computed the steps of the protocol correctly. Right, so what this is called the GMW compiler. It's 1986, 7, something like that, like super old classic work in the MPC space. But the idea is that if you take some MPC, which is semi-honest secure, and has the additional property that you get privacy but not correctness if the adversary is malicious, then you can basically apply a zero-knowledge proof, which shows that each step or each message was computed correctly by each party, and all the parties verified these zero-knowledge proofs, and you can get out a maliciously secure protocol, right? And so you have privacy and correctness against malicious adversaries up to aborts. Basically, the adversary can force the protocol to abort early, and nobody will get their result. But modulo that, you can get privacy and correctness. Now, the downside is that, as I said, these zero-knowledge proofs are very, very expensive. So what we'll try to do is we'll try to leverage this idea that the computation itself that we're doing is a ZKP, right? So if the delegator checks that the MPC, the proof is valid, right? Maybe we can get some correctness guarantees. So privacy in some sense is guaranteed by the base underlying semi-honest protocol, which we're using speeds. It has this property that you have privacy against malicious adversaries. And the correctness, hopefully, is guaranteed by the fact that if the adversary deviates non-trivially from the protocol, then the end resulting proof will sort of fail to verify. That's at least our hope, right? Like if this guy, say, switches to a completely different secret share and just discards the secret share sent by the delegator, then at the end, it'll compute like a proof for like a garbage witness. And so with very high probability, like that'll fail to verify, right? So this is the hope, right? But unfortunately, this doesn't actually work out. Okay, yeah, so that's Dara has a good point in the chat. This is actually what we use, but okay. So this approach as is doesn't quite work out, and this is because the malicious worker can sort of malleate its messages in a way that the final proof will fail only sometimes. So for example, think of an R1CS instance where you have like a Boolean constraint, right? Like x times 1 minus x equals 0. So if the original value of x was 0, right, then this constraint works out fine, and the proof will work out completely fine, everything checks out. Now I'm a malicious adversary, right? What I do is I malleate my share of x to by adding 1 to it. All right. So now if the actual value of x was 0, then the malleated value of x will be 1, right? But this will still pass the Booleanity check. So it'll still pass the x times 1 minus x equals 0, right? And so the proof at the end will still be valid. However, if the initial value of x was 1, right, then now the malleated value will become 2 because I've added 1 to it. And the Booleanity check will fail. And so the end proof will also fail, right? And so now by observing whether or not the delegator rejects on the basis of the malleation, I can figure out, okay, this bit was actually 0 or 1. And so now I've gained some information about the witness. And this is, you can sort of extend this to sort of arbitrary ranges in some sense. And you can, if there's repeated usage, like if the verifier uses the same workers again and again and the same witness again and again, maybe you can over time reconstruct large parts of the witness or the secret key or whatever that's inside your witness. So yeah, this is kind of, catastrophic for this idea in some sense. But actually, it turns out it's not actually catastrophic. What we actually need to do is we need to enforce that, okay, the adversary is using exactly the witness that I sent it, right? And it's not using sort of any malleated witness. And so what we do is we introduce this, I won't go into details, we introduce this new notion of a polynomial IOP consistency checker, which basically says that I will query the polynomials sent by this potentially malicious prover, and I'll check them for consistency in some sense with what the honest prover would have produced. Right, so I'll check that, say, the witness polynomial in Marlin or Planck actually equals like the actual witness polynomial that I would have generated as a honest prover, right? And the idea is that this is a very cheap check to make. I'm just making one query, and then I can use these PC schemes to just provide an evaluation proof for each of these queries that I make, right? Or I can do like a batch evaluation proof. And by doing this, essentially, we're sort of able to enforce that where these malicious workers, potentially malicious workers, are always using the correct witness. And sort of then what we show is that you can sort of if the verifier of the final proof accepts and this consistency checker also accepts, then we know that, okay, all of the polynomials that were used in this or generated in this protocol were actually the polynomials that would have been generated by some honest-ish prover. Like we allow like some trivial deviations. Like I don't actually care if the adversary used, say, like a different randomness in the one that it was supposed to, right? So I don't actually care about leaking like some malleation in the randomness. I do care about malleation in the witness, and that's sort of what we focus our enforcement and consistency checks on. Yeah, so this is actually, it's a bit more involved. But what we designed this consistency checker for Marlin, and what we were able to get was that we only make one additional query to the witness polynomial, and then there's a little bit of additional like linear number of multiplications for the verifier, for the delegator, to check that, okay, this witness polynomial is actually consistent with the honestly generated polynomial. But yeah, it's very cheap, and like in evaluations, adding or removing this consistency checker made no difference to the overall costs at any point, like communication. I mean, communication, yeah, even communication, delegator work, etc., etc. Okay, so this is the end of the technical section. I will very quickly go over like our evaluation and implementation stuff, and then we can wrap up. Sorry, I know I'm already 5 minutes over.
All good.
Okay. Okay, so the question is, okay, we've done a bunch of work. I've talked for an hour and a half so far. I'm tired. You're tired. Does any of this actually lead anywhere? Do we actually get concrete performance improvements from doing this work? And the answer is thankfully yes. So we actually did a bunch more optimizations in the actual protocol, like we did systems level optimizations, more cryptographic optimizations, bunch of things. And in our implementation, so basically this implementation is using ArcWorks, and it's sort of a generic, you give it like this circuit for the PIOP scheme, circuit for the PC scheme, and you will get out like a delegation protocol for the full SNARK. And we show how to, we provide some instantiations of these circuits, namely for the KZG PC scheme and the IPA scheme. Though that one right now is not giving correct results, but we should be able to fix it. And the Marlin polynomial IOP. And overall, this gives us a very efficient delegation protocol for the Marlin zkSNARK. You should be able to extend it also to Plonk. We haven't done it, but it should be doable. Maybe with a little bit more overhead compared to Marlin, but again, doable. All right. So in terms of evaluation, it is actually 20 speed up. So what we found was that we evaluated a bunch of settings, like a laptop with a very fast connection, the same laptop with like a slower connection, and then a mobile phone. And what we found was that in every case, we got quite a large speed up, like up to 26x for the phone, 9x if you have like a nice internet connection. And like, once you start sort of throttling your bandwidth, then you get like some sort of the network between the worker and the delegator becomes kind of like a bottleneck. So the improvement is less. So you're able to prove things much faster, like 6 to 26x. But also more importantly, sort of you're able to increase the size of the R1CS instance that you're able to prove by a very large amount. Like you can prove 256 times larger circuits or R1CS instances for Marlin, right? And actually, in some sense, this is more of like an artifact of our implementation. If your R1CS has this somewhat like a streaming structure, so that at the end of the circuit, I'm not like referencing variables from the beginning of the circuit, or like a lot of variables from the beginning of the circuit. Then sort of you can like get like infinite scalability at this point. So you can scale up to, like, you can sort of stream the witness secret sharing in the first phase of the delegation protocol. And sort of this can become like 1024 to 2048, like whatever number you want, you can scale up your R1CS, provable R1CS to that size. And finally, were our techniques for improving the MPC protocol actually helpful compared to prior work? And the answer is, again, we evaluated this compared with OB22. And we found that, we're at least 6x better. So that's sort of the takeaway. Thank you everyone for listening. paper is online at this right now at this ugly link, but the security proof has been very tricky to nail down because we have all these optimizations for malicious security. But now I finally have a handle on it, and it's almost done, and I'll try to push it by the end of the week, and so it'll be on ePrint soon. The code needs a little bit more work than that. Basically because the paper took so long to finalize. Everybody has moved on to better things, so it's kind of hard to get people to sit down and clean up the code. But
do you need people to review it?
The code, yeah, I mean, I think in the end, if we're not able to find time, I'll just open source it, and people can let the internet go to town on the code.
Let the internet do its thing. Yeah.
Yeah. But yeah, thank you everyone for listening, and I guess I'll take some questions that Dara had in the chat. Okay, so I guess going back to the discussion about the random oracle stuff, so I was not actually aware that like there's anything like the Halo 2 polynomial IOP was not public coin.
Oh, so it's in the permutation and lookup arguments. You sample some randomness, and then wait a minute. Do you need to do that using the? No, I don't, actually, I'm wrong. You don't need to do that using the random oracle. It's fine.
Yeah. So I think otherwise, like, you would only be designated verifier, right? Because
Yeah, that's right. Yeah.
So I think for all the SNARKs.
No, it's the prover just coming up with the randomness on its own.
Yeah, that's for zero knowledge for the permutation check, I guess. Yeah. Okay, so that's that question. Okay, and so the next question is, the delegator can maybe also check correctness up to a certain round depending on the PIOP. Yeah, essentially
I think you covered that.
Yeah, this is a consistency checker. You are sort of checking round by round. And thankfully, like it ends up being the case that at least for Marlin, you only need to check for the first round, the witness polynomial. I mean, in Plonk, there's not like a lot of multiple. Like, I think it is still 2 rounds, right? In Plonk, right?
Yes. Yeah, I'd have to check.
Yeah. Okay. So yeah, even in that case, I do think though that you would not have to check across multiple rounds. You'd be able to sort of leverage the fact, okay, the proof passed and some consistency check on the witness passed. So then everything else also sort of fits within like the acceptable parameters for the protocol.
That's not at all obvious. I can see why the security proof might have been difficult.
Yeah, I mean, like for Plonk, or like for Marlin, I can explain, right? So we have the ZA, ZB, and ZC polynomials, which correspond to like the interpolations of A times Z and B times Z and C times Z, right? And okay, you might think, okay, I actually have to check that these also are actually interpolations of A, Z, B, Z, C, Z. But what you can essentially leverage is the fact is that, okay, if I changed ZA, right, then I have this in Marlin, this so-called lin check, which checks the matrix vector product. If I change ZA to not be consistent with W, which I did check in my consistency checker, then this polynomial IOP, this lin check polynomial, would fail, right? And we know it's not failing because the SNARK passes, right? So this means that, okay, this ZA was like consistent up to randomness with the witness in some sense, and the matrix A. So that's how we're able to really minimize the number of polynomials we query on top of the sort of standard SNARK polynomials.
And so do you end up with only a single batch check?
For
Marlin.
Yes, we end up with just one evaluation proof, essentially. Okay. Yeah. Okay. All right. So yeah, then okay. So that's a high-level overview of that. So okay, leaking 1 bit is already fatal. Yes. So like, say you could, for something like Zcash, you would if you leak the bit of the key, then of the secret key, then that could be catastrophic, especially over multiple repetitions. Or like you say, you revealed, okay, the note is in like the left half of the Merkle tree, then that's 1 bit leakage, but it's completely catastrophic, like halves your anonymity set, for example.
Exactly. Yes.
Okay, so the final question is, it's not specific to R1CS. I mentioned Plonk earlier. Yeah, so we didn't implement a delegation like the circuit for Plonk. It's doable. You could, I mean, you can also like reduce R1CS to like the Plonk circuit format, and that'll also be another way to do it, and go vice versa with some overheads. Yeah, you would. Doing the work for Plonk would require a little bit more analysis, which we didn't do. But I'd be excited, like, happy to talk about it offline and see, like, well, what that would look like for Plonk.
Thank you.
Awesome. Well, thank you very much, Pratyush, for being very generous with your time. And I know you stayed up late to work on this, but this is great work, really impressive work that I think will really be helpful in terms of making use cases, real world use cases for SNARKs more practical, which ultimately I think is really going to help drive, this market that we're all kind of striving to serve. So thank you very much for coming on the show, coming on ZK Study Club. And I'll post this up on YouTube so everyone else can enjoy it. Thanks, everybody.
Yeah. Thank you so much, Alex.
Thank you.
Yeah, for having me.